start. Okay. So, what is the objective? The objective of mechanical vibration is we want to analyze, or in simple terms, understand the behavior of a system, which means a structure, an object, a body, okay, under the action of a, as I said last time, a desirable or undesirable motion. We want to do that because we want to be able to use this in an effective way, okay, at that motion in an effective way, or to eliminate that motion. So that's the objective of mechanical vibration. So as we said, we have been talking about the system. So remember in statics, if you especially took the course with me, I said the course is basically studying two things. Understanding what a force is, because the statics is what? Static is studying the action of a force on a rigid body. So we spend a good part of the course just to understand what a force is, how to represent the force, how to model the force vectorially and whatnot and so on. What is the rotational effect? What is the translational effect of force? How forces add up and whatnot. And then we looked at what a force does to a rigid body, which results in basically transmitting that applied force into either components or the support of the structure, right? In vibration, in fact, it is the system itself that is really the focus, and that is the most important part. We really need to understand what a system is. We need to understand how to model and represent the force so that we can study that under the action of this force. And there's a big difference. First of all, the force or the disturbance is, as we said, is time dependent, okay? And the system, depending how you look at it, can be simple or very complex. Of course, in reality, physical systems are complex, but as engineers, we want to turn them into something simple that we can analyze and understand. So, as I said last time again, schematically speaking, the whole course or the topic of mechanical vibrations can be demonstrated or schematically shown with this diagram and the three components that this diagram consists of. We have a force or a motion, for that matter, or disturbance. So I would call that, for the better terminology or better way of describing this input, it's called that disturbance. Because it can be a force, it can be a displacement, okay, it can be acceleration, and so on. Then we have the system and the response. So there are three elements in mechanical vibration that is the focus of our study. But as I said, the most important one is the system itself, okay? Let's call this f of t. So we present that with this function of time. that for the time being, we say that is a force. As I said, f of t is the disturbance, and it is time dependent. The system can be complex, can be simple, okay? But basically, the system is that element that has all the inherent characteristics of a real physical structure in it. And any real physical structure has, in general, as we will see, no more than 3 major inherent properties or characteristics, which are mass, or the inertia of the system, which is basically as a result of the action of the force moves in certain direction. It is the ability of the system or that structure to resist this motion, and the resistance comes in 2 distinct ways. The structure resists by going through some deformation, bending, reacting to the action of the force, which we call that elasticity. Also, that system or the structure resists the imposed motion or the force by trying to dissipate the effect of that action or dissipating energy that resists that motion. So there are 3 elements that we will talk about: mass, okay, elasticity, and energy absorption. That defines basically what any system is made of or is capable of doing in order to resist the action of an applied load. So we will talk about that, of course, in details later, but as I said at the beginning, in vibration, this really becomes a critical part. And this is the part that we will see that we need to understand and model, because that's what we are going to study. We are going to basically look at any structure in the world and be able to identify that as a system, meaning that identify what is its mass, what is elasticity, what is its energy characteristics, so that we can study that, okay? So the system is really the bridge between the real world, the physical world, and the world of mathematics, or the world of vibration, okay? In order to do that, okay, in order to basically come up with a mathematical model that would replace this, and we can really deal with it, we cannot do much with this schematic diagram. If I tell you, okay, this is what mechanical vibration is all about, and I want you to find a response of this system, how do you do this? In order to do that, you need to come up with a mathematical model, okay? A mathematical model that represents this. In order to do that, which is basically bridging the gap between the real world and the mathematical world, we need to do some idealization. Idealization meaning 2 things: making a few logical assumptions based on knowing the physics of the problem or the physics of the structure, so making a few assumptions. And also idealization means defining a few things that can make, help us or make us able to develop this mathematical model. So what kind of idealization we want to do? First of all, let's talk about the motion or the disturbance, okay? And what happens, okay? As I said, we assume that this force has certain forms or, okay, behaviors. We'll get to that, okay? So leave that for the time being. As far as the motion, as we are going to study in statics, we will be dealing with two types of motion. One is, in fact, you have seen both of them in dynamics, but in a different context and with the different objectives. But basically, these are the two types of motion we will be dealing with: translational and rotational. Okay. The main difference, can anybody tell me what is the main difference between a translational motion and a rotational motion? What is important here? What is important here? In both of them, you're talking about the mass going through some motion, right? In translational, what do? We look at the motion in terms of what is happening to the center of mass. Okay? The distribution of the mass, or the way the mass is distributed, or the inertia, not so important. In rotational motion, in fact, it is the mass distribution which is important. So, in the translational motion, we're just dealing with the mass, or the center of the mass, or how the mass is lumped at one point. In rotational motion, it is a mass moment of inertia. Which is really defining the way the motion is taking place. So these are two things that we need to know as far as the idealization and so on. So first is the type of motion we're dealing about. There is also something else about the motion or the deformation that a physical system goes through. When a structure deforms or goes through displacement as a result of an applied load, whether it's applied load is constant or time dependent, something happens to this system. And the most important thing that happens is the deformation of that system. You've seen that in the strength of material. Okay? So how do we want to look at the deformation in vibrations? In a strength of material, you saw that. You model the structure very simple. A bar, a shaft, or a beam, depending on basically what kind of force you had and what kind of deformation you were looking at. If you're looking at just the elongation, compression, or extension, okay, you consider that the structure, that piece of the structure as a bar. If you're also interested in basically rotational deformation, you looked at that piece that you studied as a shaft. If you're looking at both bending of that element and also as a shearing deformation of it, you look at it as a beam. What we do in vibration, we are interested in seeing that how this mass, or what basically this structure is made of, moves, okay? That's very complicated, right? So in order to simplify that very complex behavior, we define something called the degrees of freedom. What is a degree of freedom? A degree of freedom describes how every single mass element or molecule in a structure moves. When a structure moves, how every single point that has a mass in that structure moves. Complicated, right? it becomes much more simple when you think of it this way, that if you know that there is a dominant shape that a structure has when it goes through deformation, okay? In other words, there is a one independent deformation that the rest of the structure can be defined according to that. We call that basically a single degree of freedom. Let me make it more simple. Let's say if you look at a water tower, and this water tower, due to some motion, moves, okay? We know that physically, this is going to move like this. At least the dominant way of deformation or the displacement is this. If, of course, depending on the excitation or the force acting on that, the intensity of this motion increases, maybe other types of deformation take place. But for the most part, is this. When a tree moves with the action of the wind, it moves like this. So immediately we say, wait a minute then, if we assume that the entire mass can be assumed to be in this location, right? So the displacement that this mass goes through, okay, can describe the displacement of in other words, if we know this, we can find every single deformation at every point by just having a mathematical, basically, function that can describe this. As long as you have this, everything else can be described according to that. We call that an independent degree of freedom, and if you model this, if you think about the overall motion of a structure represented by the motion of a single point, we call this a single degree of freedom. In general, structures, especially if you think about that they're continuous, all the masses are completely connected to each other, and so on, have infinite number of degrees of freedom because every point mass in the structure is moving. But if you think of the structure made of a series of discrete masses, in other words, if you think of a tree, the mass is mainly located at the top of the tree. Or this water tower, the entire mass can be assumed to be at that location. We can think of this, the structure can be represented by a single degree of freedom which describes the motion of that. Okay? So, what else? We go back down to this motion, or what is causing the displacement or disturbance in vibration. This force can be of various shapes and various types. Okay? Okay? This force can be a harmonic force, a sinusoidal, cyclic force, okay? Like the engine of an aircraft or a car, or any rotational, cyclic motion. It can be periodic, but not harmonic, something like this, for example. And it can be none of those. It can be general, like a blast load, an impact load, things of that sort, okay? And of course, it can be completely unpredictable, which we call that, or predictability is associated with some kind of a probability associated with that, which we call that random load, like earthquake is a random load, or wind load is a random load, okay? So mechanical vibration can be categorized, or what we study can be categorized in two distinct ways. One is based on the type of force that acts on the system, okay? So the system can be either vibrating without the force acting on it. In other words, the wind has been blowing, the tree is moving, and then wind stops. But obviously the tree still continues to move. So we call that free vibration because the structure is vibrating under the action of no load. Some load existed in the past history, but it no longer exists, but the vibration continues. We call that free vibration. Or the system is vibrating due to the action of the force that continuously is acting on it and exists. We call that a force vibration. Okay. Mechanical vibration can also be categorized in a different way. We will see that. But let's, for the time being, think about all these sort of the components that will come to a picture and are basically important. Okay. So having said that, based on what we just described, which is very important, okay, is the force, the system, and the response. How do we want to come up with a mathematical model that describes what we're going to do? We said that the system is consisting of a mass, which we call that M, consists of an ability to resist deformation, which we call that elasticity, and it also consists of a basically inherent characteristics that absorbs energy or dissipates energy. Let's call that a C, okay? We also said that ideally, most structures can be assumed that they basically can be represented by a motion, especially when we are talking about the translational motion, that 1 degree of freedom can describe the entire motion of that structure. If you look at that tree, you look at the tip of the tree, you know what direction it is moving when the wind blows. So just knowing the motion of that tip of the tree can describe the motion that you're interested in, okay? If we can describe a system by a single degree of freedom, we can assume basically the entire mass of that structure is lumped in at that point, and it is that point which basically consists of the entire mass of the structure that is moving in certain direction. And as I said, this certain direction is either translational or rotational. For the time being, let's focus on just the translational motion. So basically then, a system can be assumed to consist of a mass, that this mass moves in one direction, which I call that a single degree of freedom. Then I said, as this system moves, what is resisting it? What is stopping that motion is the deformation or the elasticity of this, which is a force that can be described if we assume that the system is linear, that deformation is a function, is a linear function of that displacement, okay? We represent that, therefore, by a linear force, which is basically a spring. And then there is something else which is also resisting that motion, and we call that something else a damping, elements. So we call this the stiffness or elasticity element, and we call this a damping element, and this is the inertia or the mass. Of course, we don't have to show it this way, you can demonstrate it this way, but it's easier, of course, to show it that way, okay? But the point is that for the time being, we assume that every single structure in the world that we are dealing with can be physically modeled or be assumed that its motion can be described by the motion of a single point where the entire mass of the structure is lumped at that point. It may sound very simplistic, but believe it or not, what we have set up here, which we call that a single degree of freedom, or SDOF system, can represent almost any physical system in the world, including your own body. We will see. And of course, this system is disturbed by a disturbance, a force. So this is now the model that we are dealing with. It has the input, the force, it has represents a response, and it has a system. So, or we have now defined our system consisting of three distinct, discrete elements: the mass, the stiffness, and the damper. So now, the objective of this course becomes basically twofold. Step number one is how to model a physical system as a single degree of freedom system. In other words, if I give you a structure, how can you find what is the stiffness in that structure? What is the damping element? And what is the mass of the structure? Okay? So that's where we spend a few weeks to really be able to develop or set up this model based on the knowledge that you have. Nothing new, based on what you've learned in the strength of material, basically. That's what it comes down to, and dynamics. Okay. The second task is, okay, how to find the response. That is the displacement, or velocity, or the acceleration, or the stresses and the strains, and so on. So this is what mechanical vibration is all about. Being able to model a structure as a single degree of freedom system, and then, given the force that we know it is of what type, or no force at all, find the displacement or the response of the structure. So now that we have a schematically set up the model for the studying of mechanical vibration, let's see, dealing with these two objectives involves, how many steps or how many different categories that we will be studying, okay? Mechanical vibration can be classified or categorized in terms of what we study into the following, okay? Depending on how we look at the system. We can assume that this innocent looking system that we are dealing with, okay, is somehow does not have the ability, or if it does, that ability is negligible to absorb energy or dissipate energy. Okay? We call this an undamped system. In other words, in many cases, we can just assume that damping or that energy absorption is not important or doesn't exist or can be ignored. Or we cannot ignore that. So the system has mass, stiffness, and damping. We call this a damped system. So, as I said, the objective of the vibration is to look at this system and find the response of this system. In either case, the system can be moving without the force being constantly present on that. It may have been disturbed. As I said, the wind has blown against that tree, so the tree's moving and the wind stops, so it continues to move, right? Or, that's not a good example, but I would say that anyway, you're sitting on a swing, somebody pushes you, right? A few times, and you start basically swinging, and then that push stops, but you continue to swing. You're basically going through some free vibration. There is no force. You're just moving, right? Because of the initial disturbance. So we can say that category called free vibration. Or a force is present all the time on the system when it's moving, a force vibration. So in each of these categories, we may be dealing with either an undamped or a damped system. So studying mechanical vibration, basically studying these four cases. Undamped free vibration of a system, and damped, or the free vibration of a damped system. Force vibration of an undamped system, and the force vibration of an undamped system. And remember, of course, that that force can be either harmonic, periodic, or general. That's what we will be doing in mechanical vibration. So in a nutshell, that's basically the entire scope of what we will do in mechanical vibration. So with that said, now let's begin. Because we still haven't seen yet, what am I going to do with this? Or how we are going to find the response from this creature. Okay, so what is the tool that we are going to use in analyzing any structure? Remember statics? How did we study the behavior of any rigid body in equilibrium? What was the key tool that we used to study that? Anybody? What was the statics all about? Free body diagram. 80% of statics. Same thing here. Okay? Except that, in this case, our structure is very simple. But nevertheless, that is the tool. So, how do we go about it? You have a mass, right, which is moving, and that is your structure. That is all you have, right? So this mass is moving, going through some displacement as a result of a force acting on that, okay? So you have an external force, right, and it is moving in this direction. I said this mass is resisting the motion, or an inherent characteristic of this is that it resists this deformation in one direction due to the action of two forces. One is this force of elasticity, or the spring force, which we assume it is a linear function of the displacement. So as this goes through a displacement of u, in other words, this mass goes from here to here, okay, going through this displacement, this spring is going to be stretched the same amount, so a force of k times u is generated, which is resisting that mass, right? So that's simple, right? This other force, which we call that a damping force, is not as simple as that one. We actually fudge it, believe it or not. Because the energy dissipation is a very complex behavior. So we need to simplify that. Simplification in this case meaning making the assumption. The assumption is that we assume that the energy is dissipated in such a way that the force that represents that energy is proportional to the velocity that this system basically generates. So we say that damping force is a constant that we call that a damping coefficient times the velocity. K, we call that the stiffness coefficient. Okay. What else we have to complete this diagram? There are two ways to set up the free body diagram in dynamics, right? Or solving dynamic vibration problem. One is using somebody's laws that I do not like, that somebody. Because he was one of the biggest thieves of all time. Those who have taken statics with me know my feelings toward Mr. Newton, because he did not do anything. He just stole everything that Galileo had discovered, and then claimed that all those were his. Okay, that story about apple falling on the tree, all that is nonsense. Galileo had discovered all of that and formulated it a long time ago. So instead, I prefer actually the lumber principle. What is the lumber? I'm sure you've had it in dynamics, right? The lumber force is, in order to set up or solve a dynamic problem, okay, you treat that as a static problem by drawing the free body diagram, and on that free body diagram, you place a force, which is the inertial force, in the opposite direction of motion, mass times acceleration. Okay? If you include a de L'Alembert force, which we call this de L'Alembert force, on this diagram, which basically consists of these two forces, okay, now you have a free body diagram for this dynamic system, and you can easily write basically the equations of equilibrium, which are similar to the static equilibrium, by writing summation of forces equal to 0. By including the de L'Alembert force, summation of all forces is equal to 0, except that summation of forces being m times the acceleration, right? So let's apply the L'Alembert principle, which is this. So you have m times u double dot, right, plus c u dot plus k u is equal to f of t. This differential equation, which we call that equation of motion, is what? This is the mathematical representation of this entire system, the input and the response. Look at it. It has all the information that that schematic diagram that we set up, and the model for this schematic diagram that we set up it has the mass, it has this damping, it has the stiffness, it has the force. In other words, these three define our system. Okay? The force is the response. Is the force, the input, and U is the response that we want to find. So this equation is all we have now to worry about. As long as, remember, as long as we can set up this model, set up the free body diagram of this model, and being able to set up then this differential equation, from this point on, all we have to do is just being able to solve this differential equation. Believe it or not, the entire course is just solving this differential equation. Given different cases. First, we look at this differential equation. The right-hand side is 0. That means free vibration. There is no force. So we are dealing with a homogeneous, simple, innocent-looking, linear differential equation. Then we look at force vibration by putting it of t of different forms and different functions and trying to solve this. But that's not what this course is all about. Because this was the course on differential equation. Our main focus would be how to set up this model. How to set up model of a physical system and then convert that to this. And once you convert that to this and solve for the response, what is the meaning of that response? How do we interpret that? What kind of information that will give us and so on. So that's mechanical vibration. So see you on Friday.